Hello, everyone. My name is Naresh. I'm working with Robert Bosch GmbH. It's one of the leading automotive tier ones from Germany. And concretely, I'm working in the corporate research department of Bosch. So basically, what we do is keep an eye out for new and upcoming technologies, have a look out on automotive trends, and try to kind of predict the future problems and solve it with innovative technologies. One of the leading challenges that automotive domain is currently facing is the evolution of the in-vehicle architecture, and this is what Francesco has nicely presented in the introduction talk. And here I'm going to focus on one of the newer technologies called as programmable data plane technologies. They come from data centers. How can we take this commodity technology that's available for data center networks and try to adapt it for in-vehicle networks? So this is my agenda. So I'll also reiterate some of the trends that Francesco already referred and give a brief introduction to this programmable data planes, and then show what kind of use cases we can in automotive can we really solve with it. So this is like how the future automotive or future cars what they have to support. They are going to be more autonomous in nature, electrified. They have to support third-party services. They can be tele-driven, and so on. And along with this comes a lot of challenges. So for autonomous systems with high safety requirements, they need to have some kind of failure tolerance. So some of the systems need to be fail operational. Some of them need to have some kind of graceful degradation. There are strict QoS requirements without which the system cannot be, the vehicle cannot drive on streets, and so on. And here we'll have also in the future over-the-air updates. The overall trend is now being labeled as software-defined vehicle, which means now some kind of software that is going to define what the characteristic of the vehicle is going to be. And one of the key challenges here is to architect or to design the in-vehicular networks such that the changing applications on top can be equally supported by the network that's within the vehicle. What do we need now for such a flexible in-vehicular network? We need more bandwidth. And this is a clear trend. The entire automotive industry is working on it. We have multi-gig Ethernet. This is now also going into realms of bandwidths that's going over 25 gigabit per second and so on. Bandwidth alone is not going to help. We also need freedom from interference because it's a real-time system, so we need some kind of real-time capabilities. This is another trend that the community has recognized, and within IEEE, there's this time-sensitive networking. You'll also hear in the next talk more about it. And this TSN kind of has already almost solved this freedom from interference problem. The third thing that we need to do is to be able to adapt to changing communication patterns in the field. So as I showed in the previous slide, we'll have new applications coming down. You'll have, for instance, the autonomous driving logic that might be changed in the field. And you need to adapt to the changing applications in the in-vehicular network. And this is an open question. How do we solve it? Which technologies do we bring in here? And what needs to be done exactly for this? So we look towards data center networking because they have had similar challenges and they have almost solved it now. And one of the ways that they did use was the software-defined networking. So what exactly is that? In software-defined networking, you have a controller, which is the brain of the entire network. It kind of monitors what's happening in the network. So it's constantly looking at the events in the network. And based on these events, it's making its own picture of, hey, what do I need to do so that the network is efficient enough, optimal enough to serve all the applications that are running inside the infrastructure. Based on this, the SDN controller finally programs the underlying network. So it's basically the switches that get programmed, and finally you have implemented some kind of a control loop based on whatever is changing, what applications are changing in the infrastructure. The network changes along with it. Now there's a problem. SDN controller can only, how it monitors these events and how it kind of programs the switches is it reads some kind of registers and counters to see what kind of packets are going through the network. And based on it, it sets up some rules in the lookup tables, says which IP, which packets need to go where. And that's it. More than that, the SDN controller cannot do anything. So basically, whatever your switches can do is kind of in the silicon, and this cannot be changed at runtime by any kind of software-defined networks. Just to give an example, you might see some of these Ethernet boxes here, and they are kind of pre-programmed. The chipsets in them can only identify certain kind of packets that are going through. Usually it's IP or Ethernet frames, and basically in the lookup tables you can only say, hey, if you get a packet from a particular address, forward it on certain kind of port. You cannot now suddenly start teaching these switches new kind of protocols. And in automotive, that's kind of different, because the kind of protocols that are used in automotive are quite different from what are used in data centers or what we use in our office IT networks. How do we solve it? One approach is programmable data planes. So what programmable data, the origin of this idea of programmable data planes is, no matter what kind of switching element you have a basic kind of abstraction there. Any packet that you get, you try to extract certain fields of interest from it. Like in office networks, it would be Ethernet destination address or IP destination address. Followed by that, you have a lookup table where you check what do you do with this particular frame, and then finally execute that action. And this is exactly at a higher level what programmable data planes encapsulate. So what they have done is divided the packet processing pipeline into three parts. One is a parser, which you can program. It's a state machine. The second section is a series of match action tables. And finally, you have some kind of a deparser. So basically what happens, any packet that comes in, it goes through the state machine that you have programmed a priori. You extract the fields of interest, and this could be some IP header fields or could be your custom protocol that you extract. And finally, these fields pass through a series of match action tables before a new packet emerges at the end, and then this is sent out through the egress port. So basically what you now get is a nice abstraction called reconfigurable match action tables, against which you can program your network, and all of this is happening in hardware. P4, it's an open source initiative, so a lot of tooling that you get for P4 is already available. It's kind of a language where you can program against this reconfigurable match action table abstraction. What you see here is how simple it is now to program something like IP forwarding. I could fit the entire program in a single slide. What you see on the left side is the parser. So it's a state machine. So it goes through different states, and at the end of it, you have certain kind of fields of interest. In this case, it's the IP headers that have been extracted. You define your match action tables, which is the central field here. Finally, you have an action, and that's it, right? So if you now have come up with an idea of a custom protocol, it's rather easy to implement with this kind of modeling language. So what do we get now? We get with SDN or software-defined networking, a mechanism where you have a controller that can program the network switches, and you have with this programmable data planes another dimension, which is like the horizontal dimension, where you can also define how your packets need to be processed. So together, you can now implement in the network newer protocols, you have faster innovation, you can bring applications aware knowledge inside the networks. Networks are no longer dumb, where it's only forwarding certain kind of IP packets. You now have really application specific packets that are going through the network, and network can interpret accordingly. So now the question is, how does this help for in-vehicular networks? I mean, the programmable data plane technologies, they really come from data centers. They are provisioned for high throughput. They're not real time aware. And this is one of the questions that we took into consideration when we were looking into this technology. So here you see in the image, in this red box, a mighty programmable data plane switch. It has a backbone of 1 terabits per second. This is way beyond what an automotive network requires. The question is now, how do we fit this into this zonal architecture that Francesco mentioned in the previous talk? And the point is, even if we bring it down there, what can we gain from it? And to answer this question, I will just briefly talk about service-oriented communication. This is the new way or new trend in automotive, how software is developed. So the recent generation of automotive softwares is developed as a loose collection of services. So you have functionality that's split into smaller services, just like in a microservice architecture. And at runtime, these services kind of detect each other and communicate with each other to realize distributed functionality. So one example could be this distributed control loop that, again, was referred in the previous talk. What kind of communication protocols are used for it? Some IP, DDS, these are highly standardized protocols which are used in automotive domain. Now, the problem with this service-oriented communication is it's basically designed for an application agnostic network, so a really dumb network. And that's why, to achieve this kind of functionality where you have services discovering each other at runtime and communicating with each other, you needed to implement something like broadcast or multicast, where the entire information is flooded in the network, and services kind of can interpret each other from this broadcasted information. The question is, can we do better with programmable data planes? Because now we have this this possibility that will push the application logic into the networks using this reconfigurable match action table paradigm. For this, we have a couple of use cases. So the first one is runtime service discovery, as we call it. So what we see in automotive service-oriented communication is at least the discovery, and in some cases even the data distribution is happening on top of multicasts and broadcasts. And this means that the overhead kind of scales quadratically, because every new service that you add in your infrastructure is now going to generate additional traffic, and this kind of needs to be broadcasted to everyone else. And this happens because your forwarding is really decoupled from service awareness. Every packet that comes into the network, that's simply broadcasted. What can we do with programmable data planes? Now, if we can teach programmable data planes the communication protocol, or this service discovery mechanism, you can make the switches more smarter. Now here I have an example. You have a service S1, which is only needed by service S4 in conventional networks. All the other services will also get information about it. If you now have a service aware network, the switches will very quickly realize, hey, there's only one other guy, one other service that's interested in S1, and instead of broadcasting it, let me unicast it. That would be one way to do it. Another way, we can also put in a software-defined networking controller into the mix. It gets this information and it can do service matching at a much fine-grained level. So you can also benefit from that. The next application is, let's include fault tolerance into the network itself. Right now, what happens in systems is, if you have redundant sensors, and if the primary fails, you need to detect this at an application layer. So this happens in terms of by using some kind of feasibility checks. You can use some kind of error codes and detect this failure on the application, and then kind of switch at runtime from a primary sensor to a secondary sensor, or if you are using actuators the same way. The problem here is, this works fine. The problem is the failover time. So if you detect this failure at the application layer, it takes a while. And for autonomous systems, so now imagine you're driving at a rather high speed and one of the sensor fails. You really quickly need to switch to the fallback scenario. You have a problem because this takes a while. And what we can do now here is, we can bring this fault tolerance awareness into the network. So here you have a switch, it's getting information from two sensors. It drops the secondary sensor because primary is working. So why bother the ECU with information from the secondary one? Now, an event of failure, the switch then identifies it at the network level itself. Hey, there's no data coming from primary sensor, or there's a fault code that kind of emerged, and kind of start forwarding the secondary sensor data to the ECU, and then thus have faster failover times. And this could be critical in autonomous systems. What we can also do with programmable data planes is execute computations on incoming packets. So if you have, with this match action lookup table, one of the actions could be like, executing some kind of math on the payload, and then kind of rewrite the packet. And what can we do here is, one of your control systems, you can offload it, that's traditionally executed by the ECU, you can offload it to the network. What this does is, you have lower latencies, and you have a little less jitter, because on the ECU, this is completely done in software. If you now use programmable data planes, this is done in hardware. So the possibility of jitter kind of reduces. So what you can do is, the sensors which are streaming its data, the switches can directly interpret this data, compute on this, and directly steer the actuators with it. And this is in the end, like, improving the overall quality of control. And what we have tried here to do is to offload a couple of control algorithms, and we could very easily do PID control algorithms directly executing it on the switch. We were able to approximate it to a reasonable extent. And then the ECU is kind of doesn't need to execute this control loop, and is only dealing with updating of set points, or executes error handling in worst case scenarios. So this technology is already commodity in data centers, but not yet in automotive. What are the open questions and challenges here? So this piece of hardware is relatively complex, and anything that goes into an automotive control unit needs to satisfy stringent norms for safety, for security, and these are not yet solved. But I think we can. There's a long way to go with this technology, and these questions can definitely be solved. The other question is about security and encryption. If your data that's coming in the network is completely encrypted, then it's hard for the switches to do anything, because all the fields extracted inside the match action table are going to be encrypted, and then there's very little that these switches can do. The other question is how does this technology combine with TSN? Because there's a lot of investment that has now gone into TSN to make the entire networks real time capable, and how does this piece of puzzle fit along with the TSN technology? And finally, how about the standardization? Because currently this technology is really standardized only for data centers. We need again something like a profile for automotive. Yeah, with this, I would finally come to the conclusion. So, programmable data planes. So, I hope, I could introduce how different this technology is compared to conventional networks, or how these complement the current networking technology. This technology is really coming from data centers, but enable fully programmable networks. And in an era where we are saying, hey, the next generation automobiles are going to be software defined vehicles, I think this piece of technology can play a significant role. And there are different use cases that we can try to implement in automotive along using these technologies. But there are plenty of open challenges which need to be solved. With this, I will kind of end my talk. If I got you curious, I'm here today, so you can get in touch. We can have a chat. I'll take maybe one or two questions if there are any